In this tutorial, we are going to look at what is dynamic programming and how you can implement that in Python. Let's just quickly go over the content that we are going to follow for this tutorial. We are going to build a basic intuition about dynamic programming and on what kind of scenarios can you apply dynamic programming. Then we are going to look at dynamic programming using two approaches, which is the commonly used approaches in dynamic programming. One is the top-down approach, or also called as memorizations, and then bottom-up approach, which is also called tabulations. And we will cover this via examples. Then we will look at the difference between them and when to use which kind of approach. And then we will finally conclude the session. Great. So let us jump into a Python notebook and understand what is dynamic programming and see that in action. As usual, we will share a GitHub repositories link in which will contain this particular notebook. So let us look at the key points of dynamic programming. Okay. So it is an algorithmic approach for solving optimization problems. Okay. It breaks a large problem into smaller subproblems and takes the most optimized approach for each subproblem. So it's kind of similar to divide and conquer or algorithms. And the only caveat with this is that it remembers the solution of all the subproblems. And at any time it encounters the subproblem again, it fetches the answer from the memory rather than recalculating it. So it makes the algorithm much more efficient over divide and conquer or traditional algorithms because it just kind of stores the value somewhere, and upon next encounter of the similar subproblem, it fetches the value directly from the memory. Let us see how this kind of things are intuitively built uh, to us as a human. So if you have three ones, okay, we know this value is 3. Even if you are computing this for the first time, you will add 1 plus 1 is 2 plus 1 3. Okay. So the next time if I add any other value to it, if I say I'm adding 5 to it, so I won't go ahead and recompute the values that I have already calculated as 1 plus 1 plus 1. I will just add 5 on top of it rather than recalculating it again. Okay. So this is some kind of dynamic programming in our daily life that we have seen. And we are going to just implement that in Python and see how we can utilize the values which we have already calculated in our existing subproblems that we are going to encounter in future. Great. So let us look at what kind of scenarios can these dynamic programming approaches be applied. Okay. First, we need to have an optimal substructures. Okay. So say if we are calculating the Fibonacci series. So at any value n, we know that the value of n will be the Fibonacci value of n minus 1 plus Fibonacci value of n minus 2. So we have a definite substructure which is going to get followed across this problem, and we can find that this is going to be a recursive calls back to back. Okay, and another example just from this thing itself is another condition that needs to satisfy is we need to have overlapping subproblems. Okay, so say if you are calculating the value of Fibonacci of 5, you just will divide it value Fibonacci of 4 and 3. Again, 3 is going to divide it by Fibonacci of 2, which is going to be Fibonacci of 1 plus 0, and you have Fibonacci of 1. So since you calculated Fibonacci of 1 and 0 in order to calculate Fibonacci of 2, now that you encounter Fibonacci of 1 again while calculating the Fibonacci of 3, you need not compute it again. You can just store the value of Fibonacci of 1 somewhere and reuse the value while calculating Fibonacci of 1 over here. Okay, so we see that we have overlapping subproblems over here. So say once you have completed calculation of Fibonacci of 3, you can directly skip the entire calculations over here and place the value directly over here. Similarly, since you have calculated the value of Fibonacci of 2 already here, you can utilize that same thing while calculating the Fibonacci of 4. So if you traverse the tree and if you calculate this particular value, Fibonacci of 1, 0, you are able to get Fibonacci of 2 and 3, right? You can just skip this particular calculation. You can skip this entire calculation. You can skip this entire calculations. And now that you can have just 1, 2, 3, 4, and 5 computation in order to get Fibonacci of 5, rather than traversing all these nodes and calculating for each of the values. We are just utilizing what we have already calculated and storing in the memory and reusing that when you encounter the problem again. So let us quickly see a few lines of code and understand how dynamic programming can improve over the time complexities of traditional way of solving problems. Okay. So for this example, we're just going to take Fibonacci series. So if you're not familiar with Fibonacci series, is it starts with 0, 1, and then it adds all the previous two values to create a new value. Okay. So my next value is going to be the sum of 0 and 1, which is 1. Then the next is going to be 1 plus 1, that is 2. Then 1 plus 2, that is going to be 3. 3 plus 2, that is going to be 5. Then 8, then 13, and so on. Okay, so this is a Fibonacci series. Okay, so the traditional way of calculating is we can use a recursive calls and build a stack value on top of other. Okay, so if you give me the Fibonacci value of n, to figure out the Fibonacci value of n, say I want to figure out the Fibonacci value at the third place, which is going to be 2. I will get Fibonacci of n. I will check whether n is equal to 0 or 1. If it is either of them, we will return 0 or 1 respectively. Else, we will break this problem down into subproblems. We will calculate the Fibonacci of n minus 1 and n minus 2. And then, at some point of time, we will hit either of these two base conditions. Okay. So if n is double is equal to 0, we will return this, or if n is equal to 1, then we will return this. And by calculating this, we are creating a stack of values on top of other and breaking the problem into smaller problems. Okay, so if you want to calculate the Fibonacci value of this particular position, which is 0, 1, 2, and 3, we're going to come here, we're going to decrease the value, and then we're going to calculate the Fibonacci of 1 and Fibonacci of 0. Okay, thus we are going to calculate this particular value. Now, to calculate the Fibonacci value of 35, it will take about 9 seconds, which is quite a lot of time. And if you increase this number even further, this entire operation will increase exponentially because the time complexity of this entire thing is exponential. Okay, so over here, now let's see that we have quite a number of overlapping problems over here in this tree just for Fibonacci of 5. And you can expect this or imagine this, if we increase this number, there will be quite a lot of like this entire number of overlapping calculations that we are doing will increase dramatically. Okay, so for this, what we'll do is anytime we create or solve a particular subproblem, we'll store that particular value and reuse that in our coming positions whenever we encounter that value. Let us see how we can implement that, and that is going to be our calculation of Fibonacci numbers using dynamic programming using the top-down approach. Okay, so the first thing that you need to do is you need to have a place where you can store the value. It could be an array, or since we are using Python, and finding the value of a particular key is much more easier in dictionaries. So we will just use a temporary dictionary for this. Okay, we will just use a temporary dict, which will be a empty dict for now. Okay, then we are going to use this same particular function that we are going to use over here. I'm just going to copy paste it over this place. Okay, and I will say it 50p top down. It will have the same thing. It will have if n double is equal to 0, we will return 0. If n double is equal to 1, we will return 1. Else, what we will do is we will find this value in temp_dict. Okay, we'll try to search for this value in temporary dict. If we are able to find the value in temporary dictionary, we'll just say get value of n. And if you are not able to find, we will return -1. And if you are not able to find, what we'll do is we will recall this function and update the value at temp_dict. Okay, value of n is equal to, we will write the same function with n minus 1 plus n minus 2. Okay. Else we will return the value of 10 take 10. Okay. So I will just use this code again and see how the performance of this entire thing is changed. Okay. So now you can see it gave me the same value as what we have calculated earlier, but now it is taking a fraction of a second. From 9 seconds, it's taking a fraction of seconds because now the time complexity has reduced to linear. Okay. So this is how you can use a top-down approach of dynamic programming and store the values in a dictionary or an array and reuse that calculated value again when you encounter the similar subproblem. Okay. Now, the reason it is top-down is that we had a greater number and we are reducing that entire thing into smaller subproblems. Okay, so I had a greater problem. I am solving a smaller problem than that. Then once again, that smaller problems are broken down to a similar smaller problem. So in order to calculate, just for example, in order to calculate 35, I'm breaking this as 30 Fibonacci of 34 and 33. Then again 34 is broken down as 33 plus 32 and so on. Similarly 33 is broken down to smaller problems. And now at the very end when you get the value of 0 and 1, you start rebuilding from bottom. Okay, so you break your problem from top till down, you get a solution and then you rebuild towards top and get the final value. That's why since you're starting from the top and going to the base value, it is known as a top-down approach. Okay. So let us now look at how you can calculate Fibonacci numbers using dynamic programming using the bottom-up approach. Okay. So in bottom-up approach, you're going to calculate a particular number starting from 0 and 1. You're going to calculate the next value, which is going to be 1. Then you calculate the next value, which is going to be 2, then 3, then 5, then 8, then 13, and so onwards till you reach the value of n, which is your desired value. Okay, since right now you're moving from bottom till the last value, you're using a bottom up approach. Okay, so for this again we will just create a function fib db bottom up. We'll take a value of n. Okay, over here we are going to use a particular array in order to store the values, and as we build from bottom to up, we will store all the values and compute the next value based on a particular logic. And the logic is the value of n is going to be the value of n minus 1 plus n minus 2. Okay, since we have a guaranteed formula in order to calculate a value of position n, we are able to build this from ground till top. Okay, so let us just create an array. I'll just create an empty array of say 0 with n plus 1 elements because we're going to start from 0. Okay, now we know the value of the 0th element and the first element are going to be 0 and 1 because that is defined. Then we will build for I in range, we'll start from 2 till n plus 1. Okay, and what we will do is we will create the value of I from the previous two values, which is going to be I minus 2 plus I minus 1. Okay, and finally we are going to return the value of the last value, which is going to be n plus 1 or the last value in the array. Okay, so over here we are not using any recursion trees, so our memory calculations will be a little bit faster as well because We are not using any sort of recursive calls or stack buildings that is happening within the scene. Okay, so let us just quickly again copy this particular set of codes and paste it over here. Just say bottom up. Now let us try to calculate this. Okay, so right now again we got the same value, but right now it has also reduced the time a lot. Okay, so instead of 0011, we are right now reduced to 0.00062. Okay, which is again a change or reduction in time from the existing top-down approach. Okay, so what we have seen over here is, since we already have a formula of calculating a nth value, which we have somehow defined or got to know, we have simplified the problem, and we do not need to go to top-down approach in order to recalculate it back from scratch. So if you remember, in top-down approach, we are breaking the problem into subproblems and smaller problems. And once we hit the base condition, we are again going from zero or the ground level to the top of it. But over here, we are not doing the traversing from top to bottom and then again to top. Over here we are just building from zero to top. Okay, so this, we are not traversing a little bit more or spending much more computation. We are able to achieve the answer within a little less span of time, even than the top down approach. Okay, so finally let us look at the top down approach and a bottom up approach side by side and see which one will fit your need. Okay, so the top-down approach is similar to divide and conquer approach. It uses recursion under the hood and thus uses the stack memory. Okay, it is a little bit relatively slower than bottom-up approach. However, the intuition behind top-down approach and the ease of implementing this in your problem will be much more efficient when you compare this against bottom-up approach, because bottom-up approach is a little bit based on formula, which you might which might take a lot of time in order to formulate, and it does not uses recursion and does not in turn uses the stack memory, and thus is relatively faster than top-down approach. Okay, so in order to decide whether you want to go with the top-down or bottom-up approach, you need to figure out is whether you will be able to formulate the logic within some formula, or will you be in a position where it will be difficult to come up with a general approach or a general formula to calculate a particular entity. So in those cases, you can go with the top-down approach and use a recursive solution. But you can just store the value in a particular memory location and just reuse that value. However, if you already have the value or a particular formula well defined for your problem statement, then you can use bottom-up approach, and it will also be much more faster from top-down approach. So let us quickly summarize the session. Okay, so what we have learned is we can apply dynamic programming over problems which have optimal substructures and which have overlapping subproblems. In dynamic programming, there are two major approaches. One is the top-down approach, also called as memorizations. Over here, you build your stack tree from the from the top to ground, and you store the intermediate results or the subproblem results in your memory. And once you encounter those problems again, you just reuse them from your memory. Another popular approach is the bottom-up approach or the tabulation approach, in which is a little bit based on formulas. And if you have the correct formula at your hand, or if you are able to formulate a logic behind the scene for your problem, then this is going to be far more efficient than top-down approach. However, it might be difficult to figure out the formula uh, when you have limited time period. Okay. So with that note, this session comes to an end. If you have liked this session, please share it with your friends and peers. Please provide your feedbacks and suggestions in the comment section below.